Static suction head. When the source of the liquid being pumped is above the pump, the head pressure caused by this column acts to push the liquid into the pump. This situation is called static suction head. Static suction head is the distance in meters from the center line of the pump suction up to the liquid level being pumped. In the pump suction situation to the right, the liquid source level is 3 meters above the pump suction, so the static suction head is 3 meters. Static discharge head. When the pump is discharging to a tank located above the pump is required to overcome the head created by the height of the liquid in the vertical discharge line. The height the destination is above the pump center line is called the static discharge head. Static discharge head is the vertical distance from the center line of the pump to the free discharge of the liquid into the discharge tank in meters. Free discharge refers to the open end of the pipe discharge line or the tank level into which the pump is discharging, whichever is highest. In the included diagram, the end of the discharge pipe is higher than the tank level. Therefore, static discharge head is measured from the end of the discharge pipe to the center line of the pump. In the pumping situation to the right, the pump discharges into the tank below the tank level. So static discharge head is from the top of the tank level to the center line of the pump. In the pumping situation to the right, static discharge head is measured from the center line of the pump discharge up to the bottom of the downspout. This is because the downspout acts as a siphon to pull liquid out of the discharge line and lessen the effect of discharge head. Total static head. Total static head is the net effect that the suction and discharge static heads have on a pump performance. It is a measure of how hard a pump has to work to pump the liquid against the static head. This net effect depends on whether we are pumping from a static lift or a suction head situation. Because a pump has to work to overcome static head in both a static suction lift and a static discharge head, then in a static suction lift scenario, total static head equals static suction lift plus static discharge head. In this situation here, we have a pump in a static suction lift situation, and we can see that the total static head is the sum of the static suction lift plus the static discharge head. Example 1. What is the total static head in the pumping scheme shown? So, since it is a static lift situation, total static head equals static discharge head plus static suction lift. Static suction head is the vertical distance from the pump suction line to the end of the discharge line. So here's the end of our discharge line here. Here's the center line of the pump. So the static discharge head is 5 meters. Static suction lift is the vertical distance from the level in the source tank up to the center line of the pump suction. So static suction lift equals 4.5 meters. Total static head equals static discharge head plus static suction lift. Total static head equals 5.0 meters plus 4.5 meters. Total static head equals 9.5 meters. Total static head with suction head. Static suction head acts to push liquid into the pump and improve its performance. Static discharge head acts to resist flow. Since total static head is a measure of how hard a pump works to overcome static pressure, then in a static suction head situation, total static head equals static discharge head minus static suction head. So in the diagram here, we see static suction head helping to push liquid into the pump suction, static discharge head resisting flow from the pump, pushing down into the pump again. So the total static head is the difference between the two. Example 2. What is the total static head in the pumping situation shown? And as we can see from the diagram, it's a static suction head situation. Since it is a static head situation, total static head equals static discharge head minus static suction head. Looking at our diagram, we know that static suction head is the distance from the center line of the pump suction to the top of the level in the source tank. So in this case, we have 4 meters from the pump suction up to the bottom of the tank, plus 2 meters to the level in the top of the tank. So static suction head would be 6 meters. On the discharge side, to get static discharge head, it is again from the center line of the pump up to the top of the liquid in the destination tank, and that is 12 meters. So our total static head would be static discharge head minus static suction head, which would be 12 meters minus 6 meters, which would give us a total static head of 6 meters. Sometimes we have to convert the pressure in kPa generated by the weight of a column of liquid to static head in meters. We can use the formula static head in meters equals equivalent pressure in kPa divided by the product of G times the relative density. Example 3. A standby pump has the suction valve shut and a pressure reading on the pump discharge is 170 kPa. If the relative density of the liquid is 1.4, what is the static discharge head? Ignore vessel pressure. Okay, here's our question. A standby pump has the suction valve shut and a pressure reading on the pump discharge of 170 kPa. If the relative density of the liquid is 1.4, what is the static discharge head? Assuming the pressure on the pump discharge is due to static discharge head only, we can say static discharge head equals static pressure in kPa divided by the product of G times the relative density. Static discharge head equals 170 kPa divided by the product of 9.81 meters per second squared times 1.4. Static discharge head is 12.4 meters. So the pressure showing on the pressure gauge on the discharge of the pump of 170 kPa would be attributed to 12.4 meters of vertical height of liquid. We can use the above formula to convert static head to equivalent static pressure in kPa. Example 4. A liquid having a relative density of 2.4 has a level in the source tank of 3.5 meters above the pump suction. What is the pressure at the pump suction in kPa due to the static suction head? So, example 4. A liquid having a relative density of 2.4 has a level in the source tank 3.5 meters above the pump suction. What is the pressure at the pump suction in kPa due to the static suction head? Static suction pressure in kPa equals static suction head in meters times the relative density times g. Static suction pressure in kPa equals a head of 3.5 meters times the relative density of 2.4 times g, which is 9.81 meters per second squared. So the static suction pressure is 82.4 kPa, which means a gauge on the suction side of the pump would show 82.4 kPa due to the height of the liquid above the pump suction. Earlier, we saw how atmospheric pressure acting on the surface of the source tank can help push liquid into the pump, especially in the suction lift situation. In some cases, pumps have to remove liquids from or push liquids to vessels pressurized at a pressure greater or less than atmospheric. In the case of pressurized vessels, the pressure acting on the liquid in the vessel is changed from kPa to equivalent head pressure. The pressure in the source vessel assists the pump in moving liquid. The pressure in the destination vessel resists the pump in moving liquid. The pressure in the destination vessel minus the pressure in the source vessel is the total pressure head the pump has to pump against. If both the source and destination tanks are at or above atmospheric pressure, we can use gauge or absolute pressure to calculate the net pressure head, as long as we use both for the source and the destination tanks. Later, when calculating net positive suction head, we will be dealing with the suction side of the pump only, and absolute pressures will be used because atmospheric pressure assists in pushing the liquid into the pump. Changing vessel pressure in kPa to equivalent head in meters, we're going to look at 3 possible scenarios and 3 equations for each one. Case 1. If the liquid being pumped is water at 4 degrees C, then pressure head in meters equals vessel pressure in kPa divided by G, or 9.81 meters per second squared. So example 5. Water at 4 degrees C is pumped from a tank having a pressure of 450 kPa. What is the equivalent pressure head? Pressure head equals kPa divided by G. Pressure head will equal 450 kPa divided by 9.81 meters per second squared. So the pressure head would be 45.9 meters. Case 2. If the liquid has a relative density other than 1, the pressure head in meters equals the vessel pressure in kPa divided by The relative density times G, or 9.81 meters per second squared. Example 6. What is the total equivalent pressure head in meters in the pumping system to the right if the liquid being pumped has a density of 750 kilograms per cubic meter? Example 6. What is the total equivalent pressure head in meters in the pumping system to the right if the liquid being pumped has a density of 750 kilograms per cubic meter? Step 1. Changing density to relative density. Relative density equals the density, which is 750 kilograms per cubic meter, divided by the density of water, which is 1,000 kilograms per cubic meter. So the relative density of the liquid is 0.75. Step 2. Finding the net pressure on the discharge and suction vessels. Since the discharge vessel pressure acts to resist pumping, and the source vessel pressure acts to assist pumping, net equivalent pressure equals discharge vessel pressure minus suction vessel pressure. Net equivalent pressure will equal 200 kPa minus 125 kPa, so the net equivalent pressure is 75 kPa. Step 3. Finding the total pressure head. Total pressure head equals net equivalent pressure divided by the product of the relative density times G. Total pressure head equals 75 kPa divided by 0.75 times 9.81 meters per second squared. Total pressure head is 10.2 meters. Case 3. If the liquid being pumped is water at a temperature greater than 4 degrees C, then the pressure head in meters equals the vessel pressure in kPa divided by the relative density of the water times 9.81 meters per second squared, where the relative density of the water is 1 divided by Vf, and Vf is the specific volume for the given temperature. Example 7. What is the net pressure head in meters in the pumping system in the diagram to the right if the liquid being pumped is 60 degrees C water? Example 7. What is the net pressure head in meters in the pumping system in the diagram if the liquid being pumped is water at 60 degrees C? Step 1. Finding the net pressure in the system. The net pressure acting on the system is the 200 kPa in the destination tank minus the 125 kPa in the source tank, which gives us 75 kPa. Since this net pressure is in the direction of the destination tank, it is pressure the pump has to overcome to push liquid to the destination. Step 2. Finding the relative density of the water. From steam table 2 at 60 degrees C, Vf equals 1.0172. Relative density equals 1 divided by Vf. Relative density equals 1 divided by 1.0172. Therefore, the relative density of the water at 60 degrees C is 0.9830. Step 3. Finding the equivalent pressure head in meters. Equivalent pressure head in meters equals the kPa due to the head pressure, the net head pressure, divided by the relative density times G. Equivalent head pressure in meters equals 75 kPa divided by 0.983 times 9.81 meters per second squared. Equivalent pressure head in meters equals 7.78 meters.